So, welcome back. So, we shall be continuing our discussions on power attack. In particularly, we shall be discussing about signal to noise ratio or SNR of power traces, and we shall be using it as a guideline to compare between different architectures, as we will see in this today's class. So, to start with, as we have been discussing that in the context of AES. So, again I will be taking the example of an AES hardware and try to explain what is meant by SNR or signal to noise ratio of a power trace. So, consider that there is a register X which is being updated by an AES circuit depending on the inputs, and we observe the corresponding power traces by varying the inputs and creating a histogram or a frequency point or a frequency plot at some point of interest, say t. Okay. So therefore, right, I mean as we know that there could be different values that the state register takes. Okay. For example, if you are modeling by say some Hamming weight classes, then it can take several Hamming values. Okay. So, our power model tells us that the power values would depend on the Hamming weight, say S. Okay. So, here is a kind of a pictographic representation of the normal distribution, and if you observe carefully, what we have kind of observed in the x axis is the power values and the y axis is the frequency as in done in normal frequency plot. But you see that I have drawn like some vertical lines to indicate the possible Hamming values. Okay. Like the Hamming value S, for example, can take the value S0, can take the value S1, can take the value S2. So, what is the goal of an attacker? The goal of the attacker, right, is by using or observing this leakage, this is the overall leakage, is to be able to distinguish between these Hamming classes, right, as we have seen that it basically tries to map from the key space to say the Hamming class. Okay. So, what essentially is here is that if you see, for example, say S1, right, which is probably the most commonly occurring Hamming class. So, it could be typically, right, if you are talking an n bit class, then it is typically the n by 2 class which occurs with the maximum frequency. So, you will find that there is a nice Gaussian distribution across that vertical line. Okay. Likewise, right, there is a like internal normal distribution across all possible Hamming classes. Okay. So, now we basically try to find out in this particular diagram or in this particular distribution, we try to find out the signal component and the noise component. Okay, because as we know that the SNR is nothing but the ratio between the signal component to the to the noise component. Okay. So, we denote this particular statistic, which is variance of ELT given S, as the signal component. Okay. So, what is ELT given S? So, you see that this is the leakage. LT is essentially nothing but the random variable which is denoting the leakage at a time instance t. Okay. So, therefore, right, this leakage can again be conditioned by the corresponding value which the state register takes. Okay. Like the state register can take S0, can take S1, can take S2, whatever values. So, therefore, right, all the leakage or all the traces which are basically going say to the S1 bin. Okay. So, say basically if I partition them depending upon like what is the Hamming classes, then the average value over there is essentially nothing but ELT given S. It is the expectation of the random variable LT given S. Okay. And that essentially is the mean value. So, you can probably think is as a hypothetically, right, if this is the normal distribution around S1, then this essentially stands for ELT given S1. Okay. Likewise, this stands for say ELT given S2, these are the means of the distributions. Okay. So, then what is variance of ELT given S? So, basically, right, the variance of ELT given S would kind of indicate how far or how separated these means are from each other, and you can understand that if these means are separated, which means if these vertical lines are separated out, then they are more distinguishable. Okay. And that is why they they contribute to determining the signal component of your power trace. Okay. Likewise, you see that this is the overall leakage, right, this is the leakage that essentially has been shown here, and this is your ELT given S, as I have just said. Okay. So, if I take the if I subtract out and get LT minus ELT given S, that essentially stands for this part. Okay. So, that stands for the fact that if I like if I take this parameter LT minus ELT given S and I like make the variance of this statistic more, then that would imply in a sense that there is more overlap between these frequency plots. Okay. For example, if I take this frequency plot and if I take this frequency plot, then this essentially stands for LT minus E LT given S1, okay, and this stands for LT minus E LT given S2, okay. And if I make them more spread, that means if I make these normal distributions more spread, then this overlap region will increase, okay. Likewise, you can see here, if I take this and if I spread it out more, then this overlap region will increase, okay. So therefore, this variance, that is variance of LT minus E LT given S, essentially contributes to noise, is essentially a measure of noise. Okay, more this variance, more is the overlap between the leakage due to the target variable S, and therefore this will hinder the attack. Okay. So therefore, I mean, it is very intuitive that now we can actually define SNR as nothing but the ratio of the variance of ELT given S to the variance of LT minus ELT given S, because this stands for the signal or this measures the signal, whereas if this part or if the numerator is more, then more are the Hamming classes separable, okay. And likewise, right, if this part of the denominator is more, then there is an overlap or there is an increased overlap due to which there is more ambiguity, and that is exactly what noise does, right. So therefore, this is a measure of noise. So the SNR is a very useful metric for assessing the threat of a power attack on a given implementation, and the question is, right, how can you really evaluate in experiments, okay. And this is a very important point to understand, because you know, like when you do your experiments, you have to estimate the SNR of the power trace, okay. So suppose you have got 10,000 traces and you target a byte, say I denote it as S, depending on the Hamming weight, say, you know, like we split the trace into 9 bins, as I said that suppose I am considering only a byte of data, okay. So as I said that I am targeting a byte and the byte can take 0 to 8, that is 9 possible Hamming classes. I basically distribute these power traces into these 9 bins, okay. At a time t, therefore the ith bin consists of, you know, like P1, you know, Pi0 to Pi Ni minus 1, assuming that Ni number of traces are going to the ith bin, and then I take the average of all these values. If I take the average of these values, I get an estimation of ELT given Si, okay, because that is the ith possible class. So we calculate so I can write ELT given S equal to I also, okay. So we calculate the variance for this signal. So note that for every Hamming class, right, I will get a corresponding average, and therefore, right, I will get if there are 9 classes, right, I will get 9 points in the I will get 9 points, and therefore I can compute the variance of this distribution. I will get a distribution. I will get, because each mean itself is essentially a point on my distribution, and therefore I calculate the variance of this distribution, and that gives me my variance of ELT given S, which is the numerator of my SNR definition, okay. And now I want the denominator. I want the denominator. So what I do is I take each of these bins, okay, and then I subtract out the average of that bin, okay. So I subtract out the average of the bin, and therefore, right, I will have some raw noise. I will have a measure of the noise in each of the bins, okay. So now I basically observe this combined distribution, because every bin will have some noise values, and then I find out the variance of this overall distribution, okay, and that gives me the denominator, and I take the ratio to get the SNR, okay. So now you can actually do interesting manipulations once you have defined this SNR. For example, as we were seeing that we were calculating the correlation for doing a DPA, now we can try to relate this correlation metric with the SNR, okay. So let us see how we can do it. So LT is nothing but P determinant. As I said, this is a deterministic portion, I mean P deterministic, which I was denoting as AS, for example. This is a deterministic portion because I can control it by the input as well as the component of the key, plus N, where N stands for noise, okay. So therefore, when we are calculating the correlation, so what we are doing is we were calculating the correlation between the total leakage LT and the hypothetical power value for the ith key, okay. The hypothetical power value for the ith key is denoted as HI, Okay. So, we are calculating the correlation between Hi and Lt. So, what is the correlation between Hi and Lt? The correlation between Hi and Lt is nothing but the correlation of Hi comma P deterministic plus N. So, this Lt is nothing but P deterministic plus noise. Okay. And therefore, I can write that as nothing but the covariance of Hi and P deterministic plus noise divided by the square root of the variance of Hi and the variance of P deterministic plus noise. Okay. So, note that when I am writing this, I am basically making an assumption, because I am writing variance of P deterministic plus noise as variance of P deterministic plus variance of noise. Okay. So, I am assuming that the noise is independent of the deterministic component. I am not assuming that there is any covariance among them. Okay. And then I can write this as covariance, or the correlation of Hi comma Lt is therefore, if I see the numerator is nothing but the expectation of Hi and P deterministic plus noise, that is these two parts, minus E of Hi into E of P deterministic plus noise. Okay. And now I take this variance of P deterministic as common, and therefore, if I write square root of variance of Hi into variance of P deterministic, then this is divided by P deterministic or variance of P deterministic. So, it becomes 1 plus variance of noise divided by variance of P deterministic. Okay. And this part essentially is nothing but 1 by SNR. Okay, because this is the variance of P deterministic and this is the variance of noise. So, this is 1 by SNR. And what is this part? If you observe here, then there is an additional part which you are adding because of noise, but again, since noise is independent, you can write this pretty much as nothing but the correlation of the deterministic component of, that is P deterministic, with Lt. Okay. So, what I mean is that now, and I know that if Hi and N are independent, that means if the noise is independent, then again the covariance between Hi and N is 0, and therefore, I can write that E of Hi comma N as nothing but E of Hi into E of N. Okay. And therefore, the numerator, as we saw previously, was E of Hi comma P deterministic plus noise minus E of Hi multiplied with E of Pt plus noise. This I can write as E of Hi comma P deterministic, E of Hi multiplied with P deterministic plus E of Hi multiplied with N minus E of Hi multiplied with E of P deterministic minus E of Hi multiplied with E of N, because this E of P deterministic plus noise I can write as E of P deterministic plus E of N. Okay, I can break it up. And this, if I assume that this particular relationship, that is E of Hi comma N is equal to E of Hi into En, then there is a cancelling that I can do here, and therefore I get E of Hi comma E of Hi into P deterministic minus E of Hi into E of P deterministic. And this, if I divide by the square root of variance of Hi and variance of P deterministic, then I get that as the correlation between Hi and P deterministic, and this is divided by square root of 1 plus 1 by SNR. Okay. So, this is a very useful result, because now it tells me that I can calculate this component, that is the correlation of Hi and P deterministic. Note that this is the hypothetical power and this is the deterministic component. And note that the deterministic component you can simulate based upon your Hamming weight or Hamming leakage model. And then in order to get the actual estimate, or at least to understand better, you just have to add up this SNR component. Okay. This also tells us that the correlation and the SNR are, like if I increase the SNR, for example, then 1 by SNR will reduce, and therefore the denominator here will reduce, and therefore what will have an effect on the correlation? You will say the correlation will also increase. Okay. So, you can basically understand the relationship between correlation and SNR from this simple equation. Okay. So, this is a useful result that way. So, now what we can do is we can try to compare between like architectures. For example, let us take the DPA of, or consider the DPA on an iterative architecture. So, this is the AES round which has been repeated, and that is what we were considering. In particular, this is a parallel architecture, which means all the S boxes, all the 16 S boxes are executing in parallel. Okay. So, if you are targeting one of the S box and the other 15 S boxes are contributing to generate algorithmic noise. Okay. So, if you consider this particular architecture, we basically did a DPA attack on this. We took around 70,000 power traces, divided it into 3,000 traces, and here it shows how the guessing entropy falls with 3,000 power traces, but it plots the average guessing entropy. So, this average is done on all these 70,000 divided by 3,000 possible classes. Okay. So, basically what it means is that you get the guessing entropy for every 3,000 power traces and you plot it on the y axis with the number of observations. As you can see, around 1,500 power traces, the guessing entropy has reduced to 0, which means you know with certainty what is the key. Okay, the key has been found out. If you compare this, remember that there is an algorithmic noise here, and you took around 1,500 observations to get the actual key. If you now compare this with a serialized architecture, in a serialized architecture, this is a diagram of a serialized architecture. You see that there is only one single S box which is essentially doing the computation, and there is a multiplexer at the beginning. So, the multiplexer takes out any byte from this 120-bit register, does a processing, and then puts it back into its corresponding position. Okay. And of course, there are diffusion layers and other functionalities of an AES round. So, here in this serialized architecture, there is only one S box. So, that means that there is no algorithmic noise. When you are targeting that S box, there is no parallel S box which is also under play. Okay, because there is only one S box in the hardware. There are no parallel S boxes in the architecture. Okay. So, therefore, there is less algorithmic noise, and exactly that is what you see here when you are doing the power attack. For example, in this case, we observe the guessing entropy for 1,000 power traces. Note that this is lesser than the 3,000 power traces that we took, and here around 500 to 600 observations, the guessing entropy goes to 0, which means now the attack is faster. It is the success rate is more, the guessing entropy is reducing faster. Okay. So, you can actually do another interesting variation of this, which is called as the shuffled architecture. So, in the shuffled architecture, what you do is you basically try to randomize this select line of the multiplexer. So, basically that means that the 16 S boxes that we have in one round of AES, you do them in any arbitrary order. Okay. Because they are independent, they can be done in any order. Okay. If you do this, so then you can observe that it is an interesting countermeasure, because it does not have any negative effect on the throughput. For example, if you think of naive countermeasures, like for example adding a dummy operation that will add on to your throughput, in this case there is no penalty, negative penalty on the throughput. So, it is quite easy to implement, because you just need to make the select line in the multiplexer arbitrary. Okay. However, if you observe, you can still make, the interesting thing is that you can still make the DPA attack work. The reason why you can make it work is that if you observe the total power in the 16 clock cycles, then it still remains the same, because although you are doing them in any arbitrary order, but if you add up the power consumption for every S box, the total power in 16 clock cycles does not change. Okay. And this is a trick which you can adopt to attack shuffled architectures. Okay. So, therefore, now let us again look back and compare these architectures using SNR as my tool. Okay. So, in the serialized architecture, so let us start with the serialized architecture. So, here we observe that the power consumption, say during the 0th S box, so suppose let us consider the 0th S box computation. There are you are doing 0 to 15, So, there are 16 times that you are computing on the S box. So, you observe the power consumption, say during the 0th S box computation, you note or you compute the Hamming distance or Hamming weight depending upon your power model corresponding to the 0th S box. Note that for this we need the key. Okay. And as we know that the classes can be from 0 to 8. So, remember I told you that when you are computing the SNR, and if you are you know the key. Okay. So, this is typically done in a template setting where you basically have an access to the key, you know the key. If you do not know the key, you cannot guess the SNR in this way. Okay. So, if you note the key, then you can find out, depending upon, say you are doing from the ciphertext, you can find out the target register that you are talking about, what is the corresponding Hamming weight or the Hamming distance corresponding to that state. Okay. So, that would imply that if you take many power observations, you can basically split them into bins depending upon its Hamming class. Okay. So, therefore, now what we do is that we calculate the average of each class and say I denote it as Pi, and imagine that in a particular ith bin, say the number of values that is over there is denoted as Fi. Okay. So, therefore, the variance of ELT given S can be found out by simply taking this E of x square minus Ex whole square. So, this is nothing but I have done sigma I equal to 0 to 8 because there are Hamming classes 8, there are 9 Hamming classes 0, 1, 2, 3 till 8, and then I multiply Fi into Pi square, okay, divided by sigma of I equal to 0 to 8 Fi minus I take the mean and I square. So, this is nothing but the mean of squares minus square of the mean. Okay. So, I take the mean here, find out the mean, which is given by the ratio of sigma I equal to 0 to 8 Fi Pi divided by sigma of Fi, and I square it. Okay. So, if you take this, then you get the variance of ELT given S. Now, for the noise component, what we do is from each power trace you deduct the average Pi if the trace belongs to the ith class. So, if the trace belongs to the ith class, then you subtract out Pi. Okay. So, now you have got so for example, in the first class, say I call it as 0th class, you had F0 observations, right. In the second class, you had F1 observations, F2, F3 and so on till F8 observations. So, in the first class, if there are F0 observations, then for each of these observations we have subtracted out the mean of that particular bin. Okay. So, therefore, you again get F0 values and all of them are noise values. Likewise, in the second bin you have got F1 noise values. Okay. So, I hope that I am clear about here. So, what I mean is if you consider that these are your bins. Okay. So, you are basically drawing bins depending upon like the Hamming class. So, suppose I call this as 0 bin, this is your 1 bin. Okay. Likewise, suppose this is your 8 bin. Say I am considering that there are 9 bins. Okay. And you take your power values, and suppose here there are F0 power values which goes in over here. Here there are F1 power values, and suppose there are F8 power values. So, therefore, for all these power values here, like suppose the power values are let me call it as say T0, T1 and so on till say Tf0 minus 1. So, what I do is that I find out the average for these and then I subtract out the average from these values. Okay. So, suppose the average of this is P0. So, therefore, my processing what I do is I basically make it T0 minus P0, then T1 minus P0 like this. Okay. T of F0 minus 1 minus P0. Okay. So, like this, right, this is for the 0th bin. You have similarly for all the possible 8 bins, and then you basically find out the average of these distribution, I mean the variance of this distribution. Okay. And that essentially gives you the variance of the noise. Okay. And therefore, now you can take the ratio between them and calculate your SNR. Okay. That is the simple idea. So now with this background, right, let us move ahead and see how the frequency plot of the signal component. So, I am just observing the 0th S box of the serialized architecture and I am seeing the frequency plot. So, again note that as expected around the 4 Hamming class which occurs with maximum frequency I get a peak, okay, and therefore, I get almost a normal looking distribution. So, now you can actually do the similar thing for the SNR for calculating for shuffled architectures. Note that if you just apply the SNR in a similar way as you did it for the serialized architecture, there you will basically get a degradation of 1 by 256 because you do not, your average, right, will be reduced by 1 by 16, and if you take a square of that, because in your numerator is a variance, so it will be reduced by 1 by 256. Okay. So, rather as we have discussed, right, our attack strategy would be to basically sum up the power values for 16 clock cycles. Okay. So, therefore, right, for the shuffle scheme we compute the SNR for the total power for all the 16 S boxes. This increases as if we target only one S box, then the SNR would be 1 by 256 that of the serialized implementation. Okay. So, what we do is we sum the power values in the traces for the sample points corresponding to each of the 16 cycles okay, and then you basically find out distribute it in the Hamming class. Note that when you are adding them up, now the number of Hamming classes is not between 0 to 8, but it is between 0 to 128, because you are adding up all the individual bytes. Okay. So, if the first one is say maximum value can be 8, the second one can be 8, and so on. If you add 16 8s, then it can lead up to 128. Okay. So, you have more Hamming classes from 0 to 128. Okay. So, now if you do that and if you plot the SNR, so here is a comparison of the SNR. So, we have basically plotted the SNR with the time instance. Interestingly, you find out the average SNR for the shuffled scheme is still lesser than that of the serialized architecture, but now it is only 1/3 lesser, okay, and not like 1 by 256 as would have been if I had done the attack targeting only one byte. Okay. So, if you for example this is if you see the circle line, right, and if you compare this peak with this peak, then you will find a rough ratio of 3, which means that like in the serialized architecture the SNR is more almost 3 times more than that of the shuffled architecture, which means that the shuffled architecture essentially is able to reduce the signal to noise ratio, and therefore is more protective against a differential power attack. Okay. And that is, you can observe it from the the guessing entropy plots also. So, if you remember, like we showed that for the serialized AES we require around 600 to 700 power traces. Here it is more than 5000 power traces. Okay. So, you can see that the guessing entropy reduces, albeit much slower. Okay. And therefore, this shows that it is I would say like a better protection compared to the serialized, or is a better design compared to the serialized architecture with respect to power attacks. Okay. So, again just to conclude, this is the usual reference that I have been following. So, to conclude, what we have discussed is, we have discussed about success rate, guessing entropy, GE, which are useful quantifiable metrics to evaluate side channel attacks. We have discussed that SNR of a power trace can be used to quantify the quality of a power trace, and the correlation, which is often a very useful metric for CPA or correlation power attack, is directly proportional to SNR. Okay. And the DPA on iterative architectures, serialized architectures and shuffle architectures can be compared using these metrics SNR and GE. So, therefore, using SNR and GE, we can give comparative, we can compare between the performance of differential power attack across these architectures. Okay. So, we will see how you can like augment them and do more interesting variations of these metrics in some later class. So, thank you for your attention.